Assalamualaikum warahmatullahi wabarakatuh. So this is example 4.3 on the analysis of heat exchanger. Okay, we have around 5 questions to discuss. Okay, for first question, example 1. Okay, let's read the question first. I'm sorry, the question a bit small because I want to take a space, give a space for my solution calculation. Okay, for the first example, okay, the condensation of steam in a condenser. So steam in the condenser of a power plant is to be condensed at a temperature 30 degrees Celsius with cooling water from nearby lake, which enter the tube here of the condenser at 14 degrees Celsius and leave at 20 degrees Celsius, 22 degrees Celsius. So the surface area given, which is 45 meters square. The overall heat transfer coefficient is 2100. So this question need you to determine the mass flow rate of the cooling water needed and the rate of condensation of the steam in the condenser. So we need to know Q and also M. Okay, first thing first, we need to calculate the temperature difference. So we have delta T1 and delta T2. So basically for this condenser, the temperature of the steam at the inlet and outlet is the same. So we consider this type of exchanger is counter flow heat exchanger. Okay, for delta T1, for the counter flow, so we can use back the formula from our previous video. So delta T1 is, you can refer the formula for the counter flow heat exchanger. So TH in minus with TC out is equal to TH in is 30, TC out is 22. So the answer would be 8 degrees Celsius. So for delta T2 is TH out minus with TC in. H out is 30, C in is 14. So it's 16 degrees Celsius. Okay, after obtain this temperature difference, we need to calculate the log mean temperature difference. 30 Lm. Okay, if you forget the formula, you can refer back to my previous video or my slide. So delta TLM is equal to delta T1 minus with delta T2 over ln delta T1 over delta T2. Okay, just input the value. You will get around 11.5 degrees Celsius. So now we need to calculate the rate of heat transfer in the condenser. We can use formula Q is equal to UA delta TLM. So U given, A also given. Just substitute inside the formula. U 2100 times with 45 times with 11.5. The answer would be 1087 kilowatt. Okay. So now we want to calculate the mass flow rate of the cooling water. So basically we can use the formula of heat balance M Cp delta T. So So basically at first you need to get the properties of each of the fluid first. Okay, forgive me because I skipped that step before. So water at 30 degrees Celsius, the specific heat capacity is this specific heat capacity we need to get the average temperature. We need to get the specific heat capacity at average temperature, which is 22 plus 14 over 2. So it's around 18. So Cp at 18 you will have 4184 joule kg dot K. So for water at 30 degrees Celsius, we can get the heat of vaporization 2431 kilojoule per kg. Okay, so basically this one you can obtain from table A9. Okay, so now you have Q, you have Cp, you have the 30. Rearrange back this equation. M is equal to Q over Cp delta T. So delta T for the heat balance, basically it's occur inside this fluid flow. So delta T is between the inlet temperature and outlet temperature of the cooling water. So M is equal to 1087 over Cp 4184. Delta T 22 minus 14 . So we can get M is equal to 32.5 kg per second. Okay, if you want to determine the mass flow rate of the steam, you can use this formula. Q is equal to M H Ft heat of vaporization. So you will have 0.45 kg per second. So this is the answer for this example 1. So let's continue with example 2. So example 2 is the heating water in counterflow heat exchanger. So we have a counterflow double pipe heat exchanger. It's used to heat water from 20 degrees Celsius here to 80 degrees Celsius at a rate of 1.2 kg per second. The heating is to be accomplished by geothermal water available at 160 degrees Celsius. So here is 160 degrees Celsius. Flow rate is 2 kg per second. The inner tube is thin wall and has a diameter of 1.5 cm. So here is 1.5 cm. If the overall heat transfer coefficient of the heat exchanger is 640 watt per meter squared dot K, determine the length of the heat exchanger required to achieve the desired heating. Okay. So first thing first, we need to know the properties of these two fluids. So the properties that we need to you need to find is specific heat of water and also geothermal fluid. So for water, Cp is equal to 4.18. So for geothermal, 4.31. Okay. So now, first thing first, we need to calculate if you notice that inside here there is no information on the outlet temperature. Okay, so what we can find is the heat transfer rate at the cold water side, because we have all the information like temperature difference, the mass flow rate. So we can calculate, first we can calculate the heat transfer at the cold water side using the heat balance equation, MCP delta T. So M is 1.2, Cp is 4.18, delta T is 80 minus 20. So we will get 301 kilowatt. Okay, so this part is for cold water. So second, we define first the temperature T out here. So basically the according to the first law of thermodynamics, Q will be the same at the tube side and also at the outer tube side. So for this one is for geothermal using the heat energy balance equation, M Cp delta T. So now we have Q, M, Cp. We don't have the delta T. We just have the T inlet. So we need to find the T outlet. So we rearrange the equation first. Q over M Cp delta T is T out minus T in. So T out is equal to Q over M Cp plus T in. So substitute all the value inside here, you will get T out is equal to, okay, let me substitute first for you. I'm so sorry, this part, for this part, basically, we erase first. So for this geothermal, you need to the delta T is T in minus T out, because T in is greater as compared to T out. So the direction of the heat transfer is from the high temperature to low temperature, right? So we need to put T in minus T out. So Q over MCP. We rearrange back this equation, we will get T in minus Q over MCP is equal to T out. So substitute all the value inside here. So 160 minus with 301 over 1.2 times with, sorry, this one is 2. Let me erase. So 2 times 4.31, you will get T out equal to 125 degrees Celsius. Okay. So now, in order to calculate the length, we need the area, right? So in order to have the area, we can use this formula. Q is equal to UA delta TLM. So we have Q and U. We don't have delta TLM. We need to calculate. So let me continue here. First thing first, we have the delta T1 and delta T2. So this one is counter flow. So TH in will minus with TC out. Here TH out will minus with TC in. So 160 minus with 80 become 80 degrees Celsius. This one 125 minus with 20, you will have 105 degrees Celsius. So delta TLM is equal to delta T1 minus delta T2 over with ln delta T1 over delta T2. So substitute the value, you will get delta TLM 91.9 degrees Celsius. So we substitute inside this equation. So we have Q just now 301. You have, oh, so basically this one you need to convert the unit to, we have kilowatt, right, at this part. So you need to convert to watt. Would be so U is 640, area, the one that we need to determine, 91.9. So area become 5.12 meters squared. So for this one, the surface area is pi times d times l. So diameter given 1.5, 5.12, 1.5 cm, which is 0.015 times L. So L is equal to 109 meter. So sorry, maybe I don't know why I cannot write here. So this one is in meter. Okay, now I move to the next example, which is example 3. So example 3 on the heating of glycerin in a multi-pass heat exchanger. So for this one, okay, Okay, we read first the question. A 2 shell passes and 4 tube passes heat exchanger is used to heat glycerin from 20 degrees Celsius to 50 degrees Celsius by hot water, which enters the thin wall 2 cm diameter tubes at 80 degrees Celsius and leave at 40 degrees Celsius. So basically, for the shell part, the cold glycerin enter here with 20 degrees Celsius, leave the shell at 50 degrees Celsius, and for the tube part, we have hot water from 80 degrees Celsius to 40 degrees Celsius at the tube part. So why we call it as a 2 shell pass? Because we have one shell and second shell, 2 shell. So for 4 tube passes is 1 tube, second tube, third tube, and fourth tube. So 2 shell pass and 4 tube passes. So here, first thing first, we need to calculate the area. So I start calculate here. So we need to calculate the surface area, pi dl. So given in here, diameter is 2 cm. The length is 60 meter. So the answer would be 3.77 meters squared. Okay, so to calculate the rate of heat transfer for this heat exchanger, this shell and tubes heat exchanger, we can use this formula. Q equal to UA needs to time with the correction factor with delta T Lm for counter flow. So basically, like what I'm saying inside the previous video, if we have different type of heat exchanger other than parallel flow heat exchanger and counter flow heat exchanger, we need to times this equation with correction factor. But please remember, you need to use the log mean temperature for the counter flow. So for the counter flow, we know that delta T1 is equal to TH in minus TC out, and delta T2 is equal to TH out minus TC in. So H in is 80, C out is 50. We get 30 degrees Celsius. H out is 40, H in is 20, so 20 degrees Celsius. So calculate the delta T Lm, log mean temperature difference, delta T1 minus with delta T2 over with ln delta T1 over delta T2. So I directly put the answer. The answer is 24.7 degrees Celsius here. So remember, inside previous video, I got mentioned you can determine the correction factor using a graph. So now we refer to the graph. So we have 2 shell passes and 4 tubes. So you need to use this graph, the B graph. So first thing, basically, you need to calculate the P. Right here, P, you have T2 minus T1 over T1 minus T2. Sorry, capital small t. So basically, the capital T is referring to the cold fluid. Meanwhile, the small t is referring to the hot fluid. So for the small t, T2, is our hot fluid. Our hot fluid leave the tube at 40 degrees Celsius, minus with the inlet 80 degrees Celsius. So inlet of the cool fluid is 20 degrees Celsius, minus with outlet of the hot is 80 degrees Celsius. We will get 0.67 for P, and for R, we get T1 minus T2 over T2 minus T1. So this one is cold fluid minus with the hot fluid over with the hot fluid. We get 0.75. So here I already draw the line. So for the P, you have 0.67 around here. The gray line here, you can see the gray line here. And we have a R around 0.75. So 0.75 is in between 0.8 and 0.6. So here you can get the correction factor is around 0. So the F is 0.91. Okay, so for the case A, so we go back to the previous slide. So now we need to get the heat transfer rate for A before any falling. So at first the condition is when we neglect the falling factor. So we can directly, in here we don't they didn't provide us with the overall heat transfer coefficient. We need to calculate on our own. So U1 over Hi plus 1 over H0. So we have H1 Hi and HO, which is 25 and 160. So 1 over 160 plus 1 over 25, we will get 21.6 watt over meter squared dot K. So now Q is equal to UAS F delta T LM counter flow. So U is 21.67 times with 3.77 times with 0.9 just now, and 24.7. You will get 1830 watt for case A. So for case B, we need to calculate back, need to consider the falling factor around 0.006. Calculate back U using this formula, 1 over 1 Hi plus H0 plus with falling factor. So just input this value and falling factor value. You will get 21.3 watt over meter squared dot K. So using this equation back, but with different U, you will get Q is equal to 105 watt. So you can see here, when there is a falling factor, the rate of heat transfer will be decreased. So